Something is wrong with the visitor from another star, and it's happening faster than physics should allow. Between November 28th and December 3rd, 3i Atlas transformed from green to gold, a colour shift that standard comet models don't predict at this distance from the Sun. Gold means the gas is gone. Gold means dust dominates. Gold means, if you believe the pattern, fragmentation is next. Because we've seen this before, Comet K1 Atlas turned gold on November 22nd. It fragmented on November 29th. Now 3i is following the exact same sequence, in the exact same constellation, with the exact same timing. Coincidence? Maybe. Or maybe location matters in ways we haven't wanted to admit. Stay with us through December 19th, because we're about to watch an interstellar object either survive or shatter, and either answer will change something fundamental about what we think we know. If this story has you intrigued like it has me, subscribe and hit like so you're here when we find out if it survives or shatters. Comment with where you're tuning in from, what time it is where you are, and what you think of this new development. Part 1. The gold shift that shouldn't exist. Something is wrong with the visitor from another star. 3 weeks ago, 3i Atlas was exactly what we expected. A comet from beyond our solar system, yes, but behaving like a comet should. It glowed green, like so many comets do when they approach the Sun. That green glow comes from diatomic carbon molecules breaking apart in sunlight, releasing a characteristic emerald hue that astronomers have catalogued for centuries. It was strange, it was interstellar, but it was following the rules. Then, sometime between November 28th and December 3rd, the green disappeared entirely. In its place, observers around the world began reporting something they couldn't quite believe. The object was now reflecting a distinct brilliant gold, not yellow, not white with a yellowish tint. Gold. A warm metallic, almost burnished reflection that has no easy explanation in standard comet physics. You might think this is a trick of the camera, some artifact of imaging equipment or atmospheric distortion. Astronomers thought that too at first, but when independent observatories in Chile, Hawaii, South Africa and the Canary Islands all confirmed the same shift using different telescopes, different sensors, and different atmospheric conditions, the excuses ran out. This was real. The comet had changed colour rapidly, in a way that shouldn't happen at this distance from the Sun. Let me explain why this matters. Comet colour is not arbitrary. It tells us what the comet is doing at a molecular level. When a comet is dominated by gas emissions, particularly carbon-based volatiles, it glows green or blue. When dust becomes dominant, reflecting sunlight rather than emitting it, the comet takes on warmer tones, reds, oranges, sometimes yellow. But gold is rare. Gold suggests a very specific kind of dust grain, highly reflective, possibly metallic, possibly silicate-rich, scattering light in a narrow band that human eyes interpret as golden. It suggests the gas has fled, or frozen, or stopped outgassing entirely. It suggests the object is no longer a comet in the traditional sense. It's something else now. At 3i Atlas's current distance, roughly 1 astronomical unit from the Sun, equivalent to Earth's distance, comets should still be actively outgassing. The Sun's energy at this range is more than enough to sublimate water ice, carbon dioxide, carbon monoxide, all the volatiles that make a comet look alive. The green coma should persist, probably intensify, as the object continues its inbound trajectory. Instead, it vanished. In less than a week, the object transformed from a chemically active body to what appears to be a dust-dominated reflector. No standard model of comet evolution predicts this timing. No equation accounts for this speed. The phase angle, the angle between the Sun, the comet and Earth, was checked and rechecked. Phase angle can affect apparent colour by changing how sunlight reflects off the nucleus, but it doesn't cause a complete transformation from emission-dominated green to reflection-dominated gold in 5 days. Atmospheric distortion was ruled out when telescopes above most of Earth's atmosphere, including high-altitude observatories and space-based instruments, confirmed the same observation. Camera white balance, always the first suspect in colour anomalies, was eliminated when raw spectroscopic data showed the actual wavelength distribution had shifted toward longer, redder wavelengths, consistent with gold reflection, not green emission. Multiple amateur astronomers using backyard equipment confirmed what the professionals were seeing. This wasn't a calibration error. This wasn't observer bias. This was a real, physical change in the object's appearance, happening in real time, faster than any comet evolution model predicted was possible at this stage of approach. Comets do change colour as they approach the Sun. Typically they start out reddish when far away, reflecting their frozen, dust-covered surfaces. As they warm, they begin outgassing, producing blue and green emissions from various molecular species. As they get very close to the Sun, dust production often increases, and the reflected component can shift back toward warmer tones. But this sequence plays out over months, sometimes years, following a predictable curve based on the comet's distance from the Sun and its composition. 3I Atlas compressed what should be a months-long transition into 5 days. That's not evolution. That's something abrupt, something catastrophic perhaps, or something we've never documented before. So what phase did 3I Atlas just enter? That's the question keeping astronomers awake right now, because there is one scenario, one well-documented precedent, where a comet turns gold this quickly. It happens when the comet is about to break apart, and we've seen this exact sequence before, very recently, with an object that shares more than just a name, an object that followed the same script step by step until it shattered. Part 2. The K1 Atlas Precedent. Nobody wants to talk about. Comet C2025. K1 Atlas is not interstellar. It's a native object, born in our own Oort cloud, following a perfectly ordinary orbit. Or at least it was, until it wasn't. In early November, K1 Atlas was glowing green, cruising through the inner solar system with all the hallmarks of a healthy, active comet. Observers tracked it routinely, expecting a standard perihelion passage with predictable brightness variations and steady outgassing. Then, around November 15th, observers noticed the green fading. Not dimming universally, but specifically the green emission lines in the spectrum were weakening. The carbon emissions were dropping off. By November 22nd, the comet had turned gold. Brilliant, unmistakable gold. Observers who had been tracking K1 for weeks were stunned. Some questioned their equipment. Others immediately began comparing images to confirm the shift was real and not a processing artifact. 7 days later, on November 29th, the comet fragmented. Not explosively, not catastrophically in a single burst, but decisively. The nucleus split into at least 3 distinct pieces, each trailing its own debris field, each dimming as the weeks progressed. High-resolution images from professional observatories showed the fragments separating at speeds of several meters per second, gradually diverging as they continued along K1's original trajectory. By mid-December, K1 Atlas was no longer a single object. It was a cloud of rubble, fading into the background noise of the solar system, just another failed comet added to the catalogue of objects that didn't survive their solar encounter. Now, here's where it gets uncomfortable. 3I Atlas turned gold on roughly December 3rd. That puts it on the exact same timeline, green to gold in days. Gold to what? We don't know yet. But if the pattern holds, if this isn't coincidence, then 3I Atlas is following a script we've already seen, and that script ends in disintegration. Gold coloration in comets is rare enough that most astronomers go their entire careers without seeing it. Survey the literature, and you'll find maybe a dozen well-documented cases in the past century. It requires a very specific set of conditions. The object must lose its volatile ices faster than it sheds dust, creating a shell of reflective grains with no gas to scatter light diffusely. This usually happens to old, exhausted comets that have made dozens of passes near the Sun, gradually depleting their volatile reserves until nothing remains but refractory dust. Or it happens to comets that suffer sudden structural failure, venting all their gas at once in a massive outburst and leaving only a dusty husk behind. For 2 comets to turn gold in the same month, in the same region of sky, using the same colour profile, defies casual explanation. Scientists are careful with language. They avoid saying this caused that without ironclad proof. Pattern recognition is a dangerous tool in science, because humans are too good at finding patterns, even in random data. We see faces in clouds, conspiracies in coincidences, order in chaos. So when you ask astronomers if K1's fragmentation and 3I's colour shift are related, they'll tell you there's no mechanism, no physical process that should link the two. One is interstellar, one is native, They come from different origins, different compositions, different thermal histories. Comparing them is like comparing a wolf to a whale, because both are mammals. Technically true, but scientifically useless. Except the timeline doesn't care about taxonomy. The sequence doesn't care about origin. Green, gold, breakup. Green, gold, and now we wait. The pattern exists whether we have an explanation for it or not. And the more you stare at the data, the harder it becomes to dismiss as random chance. K1 Atlas was discovered in May 2025, giving astronomers 6 months to study it before the colour shift occurred. During that time, it behaved normally. Predictable brightness, steady outgassing, a well-defined coma and tail. Nothing in its early behaviour suggested instability. The fragmentation, when it came, was a surprise. Not unprecedented, comets fragment all the time, but unexpected for this particular object at this particular distance. If there were precursor signs, subtle warnings that the nucleus was under stress, no one caught them. Or if they did, they didn't recognise them for what they were. Now, 3I Atlas is exhibiting the same colour shift at the same stage with the same rapidity, and astronomers are searching frantically through archival data, looking for other examples, other comets that turned gold and then fragmented, trying to build a statistical case that this is a real phenomenon and not just two coincidences stacked on top of each other. So far, the data is thin. Gold comets are rare. Gold comets that fragment shortly afterward are rarer. And gold interstellar comets, sample size of 1. Until we get more data, until we track more objects through this phase, we're flying blind. But there's one more detail that makes this harder to ignore. Both objects entered the same constellation at roughly the same time. Both passed through Leo, the lion, in the final weeks of their observable trajectories. Which brings us to the question astronomers really don't want to entertain. What if location matters? Part 3. Leo. The statistical problem. Constellations are human inventions. Everyone knows this. The stars in Leo have no physical connection to each other. Regulus, the brightest star in Leo, sits about 79 light-years from Earth. Denebola, the second brightest, is about 36 light-years away. Algeba is 126 light-years distant. They only appear grouped from Earth perspective, a trick of geometry and cultural projection that dates back thousands of years to when humans first started naming patterns in the night sky. So when two comets happen to pass through the same constellation, it should mean nothing. Space is big. Comets go everywhere. Coincidences happen. But let's be precise about what we're calling a coincidence here. 3I Atlas entered Leo on November 30th. K1 Atlas was already there, having crossed into the constellation on November 12th. Both objects turned gold while in Leo. Both objects exhibited structural stress signatures while in Leo, and both objects, if 3I follows the pattern, will reach their terminal phase while still positioned against the same background stars. That's not just two objects passing through the same arbitrary region of sky. That's two objects exhibiting identical rare behaviour while in the same arbitrary region of sky within weeks of each other. Now, constellations cover different amounts of sky. Leo is neither the largest nor the smallest. It occupies about 947 square degrees of the celestial sphere, which sounds like a lot until you remember the entire sky spans 41,253 square degrees. That means Leo represents roughly 2.3% of the total sky. For one comet to pass through Leo in a given month, unremarkable. Comets wander. They cross all 88 constellations eventually. For two comets exhibiting identical rare behaviour to pass through Leo in the same month, while both turning the same rare colour, the probability starts to compress. Let's stack the odds. Gold coloration in comets, observed maybe once every few years across the entire global astronomy community. Two comets going gold in the same month, already unlikely. Both passing through the same 2.3% of sky, narrower still. One of them being interstellar, the first interstellar comet humanity has ever tracked with modern instruments exhibiting this behaviour, and the other being native but following an identical degradation timeline. At what point does the human brain stop calling this coincidence and start looking for a cause? Here's the problem. Our brains are wired for pattern recognition. Evolution favoured ancestors who could spot the predator hiding in the grass, the poisonous berry among the safe ones, the pattern that meant danger or opportunity. We see faces in clouds, hear voices in static, find meaning in randomness because that's how we survived as a species. The gambler who sees a hot streak, the analyst who sees a trend, the mystic who sees a sign, they're all doing the same thing. They're extrapolating from insufficient data. And science exists in part to protect us from that impulse, to demand rigour, repeatability, mechanism, to say, show me the physics, not the pattern. But sometimes the pattern is the physics. Sometimes the universe is trying to tell you something, and the only reason you're not listening is because the explanation sounds too strange, too localized, too much like astrology to take seriously. Astrology claims that celestial positions influence human behaviour and destiny through mystical forces. That's nonsense. But celestial positions can correlate with real physical environments if you're talking about actual locations in space, not projected patterns on the sky. So let's put astrology aside and talk about heliospheric sectors. The sun's magnetic field doesn't radiate uniformly. It forms a structure called the heliospheric current sheet, a vast rippling boundary where the sun's magnetic polarity flips. As the sun rotates, this sheet sweeps through the solar system like a spinning skirt, creating regions of different magnetic and energetic environments. Comets passing through these regions experience different levels of solar wind pressure, different charged, particle densities, different radiation exposure. It's not mystical, it's plasma physics. Now, could Leo coincide with a particularly active or unstable heliospheric sector? Could objects passing through that region of space, regardless of origin, encounter conditions that accelerate outgassing or destabilize their structure? The heliospheric current sheet wobbles. Its position shifts with the solar cycle. During periods of high solar activity, which we're experiencing now in 2025, the sheet becomes more disturbed, creating pockets of enhanced particle density and magnetic turbulence. If a comet happens to pass through one of these pockets at the wrong time, it could experience sudden heating, enhanced erosion, or increased stress on its already fragile structure. No one is claiming this yet. No one is publishing papers with that hypothesis. But it's on the table, quietly, in the back channels where scientists talk when they don't want to sound insane. Because if location does matter, if there's something about that region of space that stresses comets in a specific way, then 3i Atlas is heading into a perfect observational trap. And we're about to find out. December 19th, that's the date. That's when 3i Atlas makes its closest approach to Earth. And that's when we'll know if this pattern is real or if we've been chasing shadows. Part 4, December 19. A perfect observational trap. December 19th, 2025. Mark it, write it down, set a reminder. Because on that date, 3i Atlas will pass just 0.28 astronomical units from Earth. That's 42 million kilometres, which sounds like a lot, but in cosmic terms it's practically brushing past us. Close enough that even amateur telescopes will catch details professionals would normally need space-based instruments to see. Close enough that spectroscopy becomes trivial. Close enough that if this thing starts to fragment, we'll see it in real time, not weeks later when the data gets processed. But here's what makes December 19th truly special. It's a new moon. The moon will be positioned between Earth and the Sun, completely dark from our perspective, invisible in the sky. No lunar glare to drown out faint features, no scattered moonlight reducing contrast. Astrophotographers spend months planning shoots around new moons because the contrast advantage is so extreme. For an object like 3i Atlas, which may already be fading if it follows K1's trajectory, this darkness is everything. We won't be squinting through moonlight trying to separate signal from noise. We'll be seeing the object as clearly as ground-based astronomy allows, and the geometry is perfect. 3i will be high in the sky for Northern Hemisphere observers, well above the atmospheric murk that distorts low-altitude observations. Southern Hemisphere observers will have slightly lower angles, but still workable. Observatories in Chile, arguably the best astronomical sites on Earth, will have unobstructed views. South Africa's facilities will have prime positioning. Australia's telescopes will catch it during their night. The northern facilities in Hawaii, the Canaries, Arizona, they'll have it near zenith, the absolute best position for minimizing atmospheric distortion. This isn't luck. Well, it's partly luck, but it's also careful planning. Once astronomers realized 3i's trajectory would bring it this close to Earth, they started coordinating. Telescope time was requested, observation windows were scheduled, campaigns were organized across continents and institutions. Because opportunities like this don't come often. We've never had an interstellar comet pass this close during a new moon with this much advance warning. Oumuamua was already leaving when we found it. Borisov stayed farther out. 3i is giving us a gift if we're ready to receive it. So what are they looking for? What observations will settle the question of whether 3i Atlas is stable or doomed? First, brightness. If the object is fragmenting, its surface area increases. More fragments mean more surfaces reflecting sunlight, which typically causes a temporary brightness surge before the pieces disperse and dim individually. Astronomers will be monitoring the light curve hour by hour, watching for any sudden jumps or drops that indicate structural change. A smooth, steady light curve suggests stability. Erratic variations suggest chaos. Second, spectroscopy. If the object's composition is shifting, if new materials are being exposed, the spectral lines will change. A sudden spike in sodium, for instance, would indicate fresh material from the interior getting blasted into space. Sodium is common in cometary interiors, but usually remains locked inside until fragmentation exposes it. A drop in carbon emissions would confirm the volatile depletion theory. An increase in silicate features would suggest dust is becoming even more dominant. Every element leaves a signature, and those signatures will tell the story of what's happening. Third, morphology. They'll be looking at the shape, the distribution of light, any asymmetry in the coma or tail. A single nucleus looks different from multiple fragments, even if those fragments are still loosely bound. High-resolution imaging will reveal whether the object is intact or breaking apart. If it's fragmenting, we should see multiple brightness peaks in the same image, each representing a separate piece. If it's stable, the light distribution should remain smooth and roughly symmetric. Fourth, motion. If the pieces are separating, their trajectories will diverge slightly over hours and days. Precise astrometry, measuring the object's position against background stars to subarc-second accuracy, will catch that divergence. Even if the fragments are too close together to resolve visually, their motion will give them away. Objects that are gravitationally bound move together. Objects that are separating drift apart. What would confirm instability? A brightness surge followed by rapid fading. Multiple light sources appearing in high-resolution images. Spectral chaos. Lines appearing and disappearing as different materials vent uncontrollably. Asymmetric coma structure indicating directional outgassing from multiple sources. Diverging motion tracks showing the pieces are no longer bound. What would confirm stabilization? Steady brightness, a smooth symmetric coma, spectral consistency. No fragmentation features even under intense scrutiny. A single, well-defined nucleus that remains coherent over days of observation. Both outcomes are possible, both have precedent. Comets that looked doomed have held together. Comets that looked stable have shattered without warning. The physics is chaotic, the variables too numerous, the observational data too coarse to make confident predictions. But December 19th eliminates excuses. The observing conditions are optimal, the instruments are ready, the expertise is mobilized. If something is happening, we'll see it, and if nothing is happening, we'll know that too. But there's a third option, and it's the one scientists won't say out loud yet. What if 3i Atlas does something entirely new? What if it doesn't fragment cleanly, but instead enters some intermediate state, shedding mass sporadically, flickering in brightness, defying every model we have for comet behaviour? We've never tracked an interstellar comet this closely during a potential breakup phase. We don't actually know what to expect, and that uncertainty, that gap in our knowledge, is where the real tension lives. Because if 3i does something unexpected, it means our understanding is incomplete. An incomplete understanding means we're missing something fundamental about how these objects work. Part 5. The Unspoken Fear. Let's talk about what happens when a comet dies. Not poetically, not metaphorically, but mechanically. Comets are not solid. They're not rocks in the way that asteroids are rocks. They're piles of rubble, loosely bound by gravity and frozen volatiles, held together by ices that act as structural glue. Imagine a snowball made of gravel. The ice fills the gaps, binds the pieces, gives the structure cohesion. Now imagine heating that snowball. The ice sublimates, turns directly from solid to gas without passing through liquid, and the gas escapes. What's left? Loose gravel. No cohesion, no structure. Just pieces that happen to be close together but have no reason to stay that way. When those ices sublimate, When the sun's heat turns water and carbon dioxide directly from solid to gas, the internal pressure has to go somewhere. Usually it vents through cracks and fissures, creating jets that push material away from the nucleus in controlled bursts. These jets are visible in high-resolution images as narrow streaks, or fans of brightness, material being ejected at speeds of hundreds of meters per second. This is normal. This is how comets work. The outgassing provides a safety valve, a way for the pressure to escape without building to destructive levels. But if the outgassing becomes too rapid, if the ice sublimates faster than the gas can escape through existing cracks, the pressure builds, and when the pressure exceeds the tensile strength of the remaining structure, the comet doesn't explode. Explosions require confinement, a shell strong enough to contain pressure until it ruptures catastrophically. Comets don't have that. They're too weak, too porous. Instead, they crack. They come apart along their weakest seams, like dried mud in a desert, splitting into pieces that then continue to outgas independently. Gold coloration suggests the gas is already gone, or going. The green coma, rich in carbon emissions, requires active sublimation of carbon-bearing ices. When that stops, when the volatiles have fled or frozen or simply run out, the comet loses its glow and becomes a dust reflector. But here's the problem. If the gas is gone, what's holding the dust in place? Gravity. 3I Atlas is small, maybe a few hundred meters across, possibly less. At that scale, gravity is negligible. The escape velocity, the speed needed to leave the surface and never come back, is measured in centimeters per second. A dust grain drifting away at walking speed will never return. So if the volatiles are depleted, if the ice that once bound the structure has turned to gas and fled, what remains is a fragile shell, a thin crust of dust and rock with nothing supporting it from within. Imagine a dried sponge, fragile, brittle, full of voids where water used to be. Now imagine spinning that sponge and heating it unevenly. The sun's radiation heats one side more than the other. The spin creates centrifugal forces. The uneven heating creates thermal stress, expansion on the hot side, contraction on the cold side. The structure can't hold. It fractures, not from external impact, but from internal stress. This is the thin crust hypothesis, and it's terrifyingly plausible for objects like 3I Atlas. If 3I is already in this state, if the gold colour marks the transition from active comet to structural relic, then the object is already doomed. Not today, not necessarily tomorrow, but soon. The only question is timing. How long can a dust shell, weakly bound and internally stressed, hold together before the accumulated strain becomes too much? And December 19th will be the day we watch it happen, if it happens. Or the day we realise our fears were unfounded, and the object is more resilient than we thought. Scientists hesitate to say this publicly because fragmentation predictions are notoriously unreliable. Comets that look stable disintegrate without warning. Comets that look doomed hold together for years. The physics is chaotic, the variables too numerous, the observational data too coarse to feed into models with any confidence. You can calculate tensile strength, estimate sublimation rates, model thermal stress, but all of that assumes you know the internal structure, and we don't. We can't see inside, we can only guess based on density estimates, light curve behaviour, and comparisons to other objects that may or may not be similar. But privately, in emails and conference back channels, there's concern. K1 Atlas fragmented 7 days after turning gold. 3I turned gold on December 3rd. 7 days would be December 10th. We're past that now, and 3I is still intact. Does that mean it's safe? Or does it mean the clock is running differently? That the interstellar origin changes the timeline? That we're simply watching a slower version of the same collapse? No one knows, and that's the fear. Not that 3I will break apart. We've seen comets fragment before, it's routine. But that we won't understand why. That an object from another star carrying information about another stellar system will disintegrate before we can decode what it's trying to tell us. The gold colour, the Leo coincidence, the K1 parallel are all clues to something larger, some process we haven't named yet. If 3I fragments, we lose the evidence. If it holds together but we can't explain the colour shift, we've learned something but not enough. Either way, we're left with incomplete answers, and incomplete answers are what keep scientists awake at night, wondering if they missed something, if they asked the wrong questions, if the universe just gave them a gift and they failed to recognise it. There is no threat to Earth. Let's be absolutely clear. 3I Atlas is tiny, distant, and even if it shatters into a million pieces, none of them are on a collision course with us. The closest approach is still 42 million kilometres, more than 100 times the distance to the Moon. This is not an extinction event. This is not a Hollywood disaster, but it is a scientific moment, a chance to see something no human has seen before, an interstellar object in crisis or transition, revealing itself at close range during optimal observing conditions. We get one shot at this, and the clock is ticking. But before we can understand why it might break, we need to understand what it's made of. And that's where the chemistry gets truly strange. Part 6. The nickel without iron problem. Spectroscopy is how we read the universe. You take the light from an object, split it into its component colours using a prism or diffraction grating, and examine the resulting spectrum for dark lines or bright emission features. Each element absorbs or emits light at specific wavelengths, creating a unique fingerprint. Hydrogen has its signature lines, oxygen has its signature, iron has its signature. When you point a spectrograph at a comet, you're essentially asking, what are you made of? And usually the comet answers in predictable ways. Water, carbon monoxide, carbon dioxide, ammonia, methane, all the usual volatiles we've catalogued in hundreds of comets. Dust grains containing silicates, sometimes iron-rich minerals, sometimes magnesium. You build a chemical profile, compare it to other comets, and classify the object accordingly. 3I Atlas's spectrum looked normal at first. Water emissions, check. Carbon compounds, check. Sodium, magnesium, the usual suspects, all present in amounts consistent with typical cometary composition. Then, in late November, instruments at the European Southern Observatory's Very Large Telescope detected something unexpected. A strong emission line at 352.4 nanometers. That's atomic nickel, vaporized and glowing in sunlight, not unusual on its own. Comets sometimes carry trace metals that get vaporized when solar heating becomes intense enough. What shocked the researchers was what came next. Or rather, what didn't come next. The iron line, which should appear right next to nickel in the spectrum, was absent. Completely absent. The spectrum showed nickel but no iron. Observers double-checked their calibration. They reran the data reduction. They looked at archival observations from other telescopes to see if they'd missed something. Every instrument told the same story. Nickel, strong and clear. Iron, nowhere. In nature, nickel and iron are inseparable. They form together in the cores of dying stars, where temperatures and pressures are high enough to fuse lighter elements into these metals through nucleosynthesis. When massive stars explode as supernovae, they scatter this material across space, seeding the interstellar medium with both elements in roughly consistent ratios. When asteroids and planets form from this enriched material, nickel and iron clump together, forming alloys. Earth's core is primarily iron with about 5% nickel. Meteorites show similar ratios. When you find iron, you find nickel. When you find nickel, you find iron. The ratio varies depending on formation conditions and thermal history, but both are present. Always, except here. Here, nickel appeared alone, strong and clear, with iron nowhere in the spectrum. That's not just unusual. That's chemistry behaving in a way that has no obvious explanation in standard comet science. So what could cause this? One hypothesis, gaining traction among spectroscopists, involves metal carbonyls. These are compounds where metal atoms bond with carbon monoxide molecules, forming volatile, low-temperature gases. The most famous example is nickel carbonyl, nickel tetracarbonyl to be precise, with the chemical formula NiCO4. This compound is notorious in industrial chemistry because it forms easily and vaporizes at room temperature. At just 43 degrees Celsius, it boils. That means in the temperature range comets experience in the inner solar system, nickel carbonyl can transition from solid to gas directly, sublimating like water ice but at much lower temperatures. Iron carbonyl also exists, iron pentacarbonyl with the formula FeCO5, but it's less stable. It decomposes more readily under solar radiation, breaking apart before it can produce strong emission lines. So here's the scenario. Somewhere in the outer reaches of 3I's home stellar system, carbon monoxide gas and metallic nickel interacted under cold, low-pressure conditions, forming nickel carbonyl. This compound froze into the comet's structure, survived the interstellar journey for tens of thousands or millions of years, and is now vaporizing as the sun heats the nucleus. Iron, if it was ever present in metallic form, didn't form a stable carbonyl. It stayed locked in solid mineral grains, never reaching the gas phase, never producing a spectral emission line. This explains the observation, but it opens a stranger question. Why would 3I Atlas have the right conditions to form nickel carbonyl, but not preserve iron carbonyl? What kind of environment favours one but not the other? And what does this tell us about the star system where this object was born? If the carbonyl hypothesis is correct, it means 3I formed in a region rich in carbon monoxide, cold enough for metal carbonyls to condense, but thermally processed enough that free metallic nickel was available to react with the CO. That's not the pristine icy cloud we associate with standard comet formation in the outer reaches of a young stellar system. That's a baked, chemically evolved environment. That's a region that's been heated, possibly multiple times, possibly by stellar radiation from a nearby massive star or by shock waves from stellar winds. Free metallic nickel doesn't just appear naturally in cold molecular clouds. It has to be liberated from silicate minerals through heating or chemical processing. This suggests 3I didn't form in a quiet, stable region analogous to our Oort cloud. It formed somewhere more violent, somewhere closer to its parent star or in a region affected by nearby stellar activity. It's been processed, altered, cooked, and that has profound implications for understanding where this object came from and what its home system looked like. But we'll get to that. First, we need to talk about what thermal processing actually means and why it matters so much for understanding 3I's current behaviour and its ultimate fate. Part 7. The Baked Core. Origin Story. Pristine is a word astronomers love. It means untouched, unaltered, fresh from the primordial cloud that birthed the solar system. When we study comets from the Oort cloud, long-period comets making their first passage into the inner solar system, we're hoping to find pristine material, ices and organics that have been frozen in stasis since the solar system's formation 4.6 billion years ago. It's like opening a time capsule sealed during the birth of our planetary neighbourhood. These objects can tell us what conditions were like back then, what chemicals were available, what temperatures and pressures shaped the early solar nebula. But not all comets are pristine. Some are thermally processed, meaning they've been heated, melted, refrozen, or otherwise altered by stellar radiation, or repeated passes near the Sun. These objects lose their volatiles gradually with each perihelion passage. They shed their icy mantles layer by layer, until what remains is a rocky, desiccated core wrapped in a thin veneer of refractory dust. They're exhausted, used up, spent. Short-period comets, the ones that orbit the Sun every few years, show this clearly. They fade over time, losing brightness with each pass, until eventually they stop outgassing entirely and become indistinguishable from asteroids. We call these objects defunct comets, or dormant comets, and they populate the inner solar system by the thousands, invisible except when we happen to catch them passing nearby. 3I Atlas looks thermally processed. Not partially, completely. The nickel carbonyl chemistry suggests it formed in a carbon monoxide-rich environment, which is typical of regions near young stars where ices are condensing, but also being irradiated by intense ultraviolet light and stellar winds. The lack of pristine, volatile-rich behaviour suggests the object has been roasted, either by its parent star over long timescales as it orbited in the inner regions of its home system, or by some other heating event we can't yet identify. This is consistent with what researchers are calling the baked core hypothesis. The idea is that 3I Atlas is not a young comet freshly ejected from a stable Oort cloud, equivalent in another stellar system. It's an old comet, possibly ancient by cometary standards, that has already survived multiple close passes to its home star and was ejected late in its life cycle. By the time it got kicked into interstellar space through gravitational interactions with a massive planet or stellar companion, it had already lost most of its volatiles. The light, fluffy ices were gone, sublimated away over repeated solar encounters. What remained was a dense, rocky core, possibly with some trapped volatiles deep inside but largely depleted of the materials that make comets bright and active. This is wildly different from Borisov, the second confirmed interstellar comet that passed through our solar system in 2019. Borisov looked fresh, active, and chemically similar to solar system comets. It outgassed vigorously, maintained a bright coma and prominent tail, and showed spectral signatures consistent with pristine, unprocessed ices. Observers tracked it for months and concluded it was essentially indistinguishable from our own long-period comets. It could have formed in our solar system, and no one would know the difference based on composition alone. Borisov was pristine. 3I Atlas is not, and that difference matters profoundly, because it tells us something about the diversity of objects being ejected from other star systems. If most interstellar comets are like Borisov, young and volatile rich, then they're coming from stable, well-behaved stellar systems, where comet formation follows predictable rules analogous to our own solar system's history. But if objects like 3I exist, old and thermally processed, it means some systems are violent, chaotic, ejecting debris not just from their outer clouds, but from their inner regions. It means planetary migration is common, giant planets wandering inward and scattering material as they go. It means the process of planetary system formation is messier, more dynamic, more destructive than we might have assumed based solely on our own relatively calm solar system. Our solar system's architecture is actually unusual by current estimates. Our giant planets are far from the Sun, stable in roughly circular orbits, not causing chaos in the inner system. But many exoplanetary systems show giant planets in tight orbits, very close to their stars, likely because they migrated inward after forming farther out. That migration would have scattered countless smaller objects, some into the star, some into interstellar space. If 3I came from such a system, it might have formed in the outer reaches but then got thermally processed during a close pass before being ejected. Or it might have formed in the inner system, been processed by the star directly, and then got scattered outward by a migrating giant planet. Either way, the baked core hypothesis explains why 3I behaves the way it does. It's not supposed to be active anymore. It shouldn't have much gas left. The fact that it showed any green phase at all suggests there were still some volatile rich pockets, maybe water ice trapped in shadowed craters or deep pores that finally got heated enough to sublimate. But those pockets were small, limited, easily depleted. Once they vented, the object reverted to what it fundamentally is, a thermally processed core wrapped in refractory dust. And there's one more clue that 3I is exhausted, one more layer to this story: the interstellar frost. Part 8. Interstellar frost. The disappearing coat. Space is not empty. Popular media often depicts the void between stars as absolute nothingness, a perfect vacuum where nothing exists, but that's not true. Between stars there's gas, thin but measurable, primarily hydrogen and helium, but also more complex molecules. There's dust, microscopic grains of silicates, carbon, frozen ices. There are organic molecules, complex carbon-based compounds formed through chemistry that occurs even in the cold depths of space. There's radiation, cosmic rays and photons from distant stars permeating everything. It's a sparse medium, far less dense than the best vacuum humans can create in laboratories, but it's not nothing. When an object spends thousands or millions of years crossing the void, moving at tens of kilometers per second relative to the local interstellar medium, it collides with this material constantly. Dust grains stick to the surface. Organic molecules condense onto exposed ice. Water molecules, liberated from other icy bodies through collisions or photodissociation, freeze onto the surface wherever they make contact. Over time, the object accumulates a frost layer, a coating of interstellar material that wasn't part of its original composition when it left its home system. This frost carries the chemical fingerprint of the space it travelled through, recording a history of the journey in frozen molecules. This is why Oumuamua looked red when we first detected it. Observations showed a distinctly reddish hue consistent with organic rich material accumulated during its interstellar journey. This is why Borisov had organic signatures in its spectrum that were slightly different from typical solar system comets. The interstellar frost had modified its surface chemistry, and this is why 3I Atlas was red when we first detected it back in August 2025, when it was still far from the Sun, beyond the orbit of Mars, barely active. Then, as it moved inward and crossed the waterline, the boundary where solar heating becomes strong enough to consistently sublimate water ice, the colour began to shift. The waterline sits somewhere between 2 and 3 astronomical units from the Sun, depending on the object's reflectivity and spin characteristics. When 3I crossed that threshold, solar radiation intensity increased enough to start vaporizing the accumulated water frost. First, the colour shifted to white, as water and carbon dioxide outgassed and scattered light diffusely in all directions. The object gained a coma, a fuzzy envelope of gas and dust surrounding the nucleus. Then it shifted to green as carbon-bearing molecules, particularly diatomic carbon C2 and cyanide CN, broke apart under ultraviolet radiation and emitted their characteristic glow. And now, gold, as the frost has boiled away entirely, and we're seeing the underlying nucleus, bare and reflective, stripped of its volatile mantle. This sequence makes perfect sense if 3I is a layered object. Interstellar frost on the outside, accumulated during its journey. Thermally processed core on the inside, depleted of volatiles long before it ever left its home system. The sun's heat strips away the frost first in the outermost layers, revealing the green phase as volatiles vent from slightly deeper layers. Then those volatiles run out, the frost is gone, and all that's left is dust, heavy silicate or metallic grains that reflect yellow-gold light because they're too large to scatter blue wavelengths efficiently. This is not a chemical transformation, it's a physical shedding. The object is molting, losing its outer layers like a snake shedding skin, exposing what it was before it ever entered interstellar space. We're witnessing the removal of a temporary coating and seeing the permanent structure underneath. And that permanent structure is not a healthy active comet. It's a relic, a dormant core that briefly woke up when solar heat penetrated the frost layer, but is now reverting to quiescence. But here's the unnerving part. If we're now seeing the bare nucleus, if the frost is gone and the deep volatiles are depleted, then 3I Atlas is structurally vulnerable. The frost layer, thin as it was, provided cohesion. Water ice, even in small amounts, acts as cement, filling gaps between dust grains, binding particles together. Without it, the nucleus becomes a loose aggregate, a rubble pile held together only by the weakest gravity imaginable. At 3I's estimated size, a few hundred meters across, the escape velocity is maybe half a meter per second. A dust grain drifting away at the speed of a slow walk will never return, and that makes fragmentation not just possible, but likely. Not because of external forces, no asteroid impact or massive solar flare, but because the object can no longer hold itself together against the accumulated stresses of its own rotation, thermal expansion, and the last gasps of internal outgassing. It's dying not from violence, but from exhaustion, from having nothing left to give. So we return to the central question. Will 3I Atlas break apart? And if so, when? Part 9. Fragmentation theory versus survivability theory. Two camps have formed quietly in the astronomy community, not publicly, not in press releases or formal position papers, but in the margins of conference talks and private correspondence among researchers tracking this object. One camp believes 3I Atlas is already fragmenting, that the gold colour is the last phase before disintegration, that December 19th will confirm the breakup, and that we should be preparing to track multiple fragments as they diverge along slightly different trajectories. The other camp believes the object is stabilising, that it has shed its volatile outer layers and is now settling into a dormant state, that it will pass Earth intact and fade into the outer solar system as a quiet, inert body like Oumuamua did. Both camps have evidence. Neither can prove their case yet, and both are watching the same data, interpreting it through different frameworks. The fragmentation camp points to K1 Atlas as their primary evidence. The timeline is too similar to ignore. Green to gold in days, gold to break up in a week. If 3I follows that script, it's already overdue by their calculation, but comets don't always follow precise schedules. The breakup could be delayed by internal structure we can't see, by different rotation rates, by compositional variations. But the pattern is there. They also point to the rapid colour change, which suggests sudden, catastrophic loss of volatiles rather than gradual depletion. Gradual changes should take weeks or months. This took 5 days. That implies structural failure, a sudden venting event, possibly a collapse of internal voids that release trapped gas all at once. They also note the faintness. 3I is dimmer than expected for an object of its estimated size based on initial brightness measurements. If you calculate what the absolute magnitude should be given its distance and assume it's intact, the numbers don't quite match. It's about half a magnitude dimmer than predicted, which could mean it's already losing mass, already breaking into smaller pieces that haven't separated far enough to resolve individually yet, but are reducing the total cross-sectional area reflecting sunlight. Or it could mean our initial size estimate was wrong, and the object was always smaller than we thought. But the fragmentation camp favours the first interpretation. The survivability camp counters with size and composition arguments. 3I Atlas is denser than K1 was, based on its light curve behaviour and how it responds to solar radiation pressure. Denser objects are more resistant to tidal stress and internal pressure buildup. It's also thermally processed, which means it's already been through the fire and survived. Objects that have been roasted by their home star develop hardened crust through sintering, a process where repeated heating and cooling cycles cause the surface grains to partially fuse together, creating a more cohesive structure than pristine, fluffy material. K1 was pristine, fragile, vulnerable like fresh snow. 3I is not. It's more like packed ice, harder to break apart. They also argue that the gold colour could represent a stable end state, not a precursor to breakup. If the object has lost its volatiles and is now just a dusty reflector, there's no internal pressure to drive fragmentation. It's inert, and inert objects don't fragment without external stress like a collision or extreme tidal forces from a very close stellar passage. Since 3I isn't encountering either of those conditions, there's no mechanism to break it apart. It should simply continue along its trajectory, gradually fading as it recedes from the Sun, eventually becoming too faint to track but remaining intact. Who's right? We don't know. And that's the frustration gnawing at everyone involved. We've never tracked an interstellar object through this specific phase before. Oumuamua was already inert when we found it, showing no signs of active outgassing, already in a dormant state. Borisov stayed active throughout its entire passage through the inner solar system, maintaining its coma and tail until it receded beyond observable range. 3I is giving us something new, a transition state we've never documented in an interstellar context, and we're watching it unfold in real time without a clear model to guide us. December 19th will settle this, one way or another. Either the object holds together, brightness remains steady, no fragmentation features appear, and the survivability camp is vindicated, or the object begins to fragment. Multiple brightness peaks emerge in high-resolution images, the pieces start diverging, and the fragmentation camp was right. Or, and this is the terrifying third option, it does something entirely unexpected, and both camps are wrong because we're still fundamentally misunderstanding what we're looking at. But there's a fourth layer to this debate, one that neither camp talks about openly, but that hovers in the background of every discussion. What if the environment matters? What if something about Leo or the heliospheric sector or some localized energetic condition we haven't identified yet is actively stressing the object? What if 3I's fate is not determined solely by its internal composition and thermal history, but by external factors related to where it is right now, in this specific region of space, at this specific time? Part 10. The non-random hypothesis. Let's talk about heliospheric sectors without pretending they're mystical or invoking anything beyond established plasma physics. The Sun rotates every 27 days on average, though different latitudes rotate at slightly different rates because the Sun is not a solid body. As it rotates, its magnetic field, which is not symmetric and certainly not uniform, sweeps through the solar system like a rotating lawn sprinkler. This creates regions of varying magnetic polarity, radiation intensity, charged particle density, and solar wind pressure. These regions are real, measurable, and routinely affect spacecraft, satellites, and any object travelling through them. They're called heliospheric sectors, and understanding them is critical for space weather prediction and spacecraft operations. Now, constellations are human inventions, arbitrary groupings of stars that have no physical significance. The stars in Leo have no gravitational connection to each other, no shared motion through space, no physical relationship whatsoever. They're just bright stars that happen to lie in roughly the same direction when viewed from Earth. So in principle, saying two comets exhibited similar behaviour while in Leo should be no more meaningful than saying two people got sick while walking down Main Street. Correlation without causation, coincidence without mechanism. But sky regions defined by Earth's perspective can still correlate with heliospheric geometry if the timing happens to align in specific ways. If a comet passes through a particular region of sky, while that region also happens to correspond with a high-activity heliospheric sector, during that specific time period, the comet experiences more intense solar wind, more charged particles, more radiation pressure, more magnetic turbulence. Could this accelerate outgassing from surface ices? Could this destabilize a fragile nucleus already under internal stress? Could this explain why two comets, one interstellar and one native, both turned gold in the same sky region, within weeks of each other? This is not astrology. Let's be absolutely clear. Astrology claims that celestial positions influence human behavior and destiny through mystical, undefined forces with no physical mechanism. That's nonsense, and no scientist is suggesting otherwise. But asking whether position in space at a particular time coincides with measurable environmental factors we already know exist, that's a legitimate scientific question. It's no different from asking whether hurricanes are more likely during certain seasons, or whether solar flares cluster during certain phases of the solar cycle. Pattern recognition becomes meaningful when you can propose a physical mechanism. The problem is that suggesting environmental triggers for comet behavior sounds too much like claiming the stars influence our fate. It sounds unscientific even when the hypothesis is grounded in real plasma physics and magnetic field interactions documented by decades of spacecraft observations. So astronomers avoid it. They focus on intrinsic properties, composition, structure, thermal history, anything internal to the object. Those are safe topics, well-understood frameworks with established models. But what if some behaviours are fundamentally extrinsic? What if the environment plays a larger role than we've been willing to admit because acknowledging it sounds too much like validating superstition? 3i Atlas is the test case. It's passing through Leo during a time when solar activity is elevated. We're currently in solar maximum, the peak of the 11-year solar cycle, when sunspots are abundant and coronal mass ejections are frequent. The heliospheric current sheet is more disturbed during solar maximum, creating enhanced turbulence and stronger sector boundaries. 3i is positioned in a region of sky that, during this specific time period, may coincide with a particularly active heliospheric boundary crossing, and it's exhibiting behaviour that simple internal-only models struggle to explain. If it fragments on December 19th, while still in Leo, while still in this specific geometric relationship to the Sun's magnetic structure, the non-random hypothesis gains weight. Not proof, but weight. If it waits until it's moved out of Leo and into Virgo, crossing into a different heliospheric sector, or if it never fragments at all and stabilizes once it clears this region, we learn something different but equally important. Either way, the data matters. But this is where science meets epistemology, the philosophy of what counts as knowledge. How do you investigate a hypothesis that only makes sense if you expand the definition of what counts as relevant context? How do you study environmental effects on comet stability without being accused of promoting cosmic determinism or giving ammunition to astrological thinking? You don't, usually. You wait for the data, you publish cautiously in specialized journals where only experts read, and you let the next generation of researchers decide if the pattern was real or just noise that looked meaningful in hindsight. And that's frustrating because we're living through the event right now. The data is being collected this week, and the answers feel tantalizingly close. We have better instruments than ever, better models, better understanding of heliospheric physics. If there's an environmental component to comet behavior, now is when we could detect it. But science moves slowly, carefully, demanding multiple lines of evidence before accepting new frameworks. And maybe that's good. Maybe that caution has saved us from countless false leads and dead ends. But it also means that sometimes we watch the universe hand us clues and we're not quite ready to pick them up. So we watch, we wait, and we prepare for December 19th, knowing that whatever happens, it's going to teach us something. Part 11. Interstellar objects are getting weirder, not rarer. In 2017, we discovered Oumuamua. The name means scout or messenger in Hawaiian, chosen because the Pan-STARRS telescope that found it is located in Hawaii, and because the object was indeed a messenger, the first confirmed visitor from another star system. In 2019, we found Borisov, named after the amateur astronomer who spotted it using a homemade telescope from Crimea. In 2025, we found 3i Atlas, detected by the Asteroid Terrestrial Impact Last Alert System survey. That's 3 interstellar objects in 8 years. For context, we had found 0 before 2017. 0. In all of human history, despite centuries of telescopic observation dating back to Galileo in 1610, we never confirmed a single visitor from another star until Oumuamua tumbled through our solar system. And now we're finding them every few years, Maybe faster as surveys improve. What changed? Detection improved. Dramatically. Modern survey telescopes like Pan-STARRS, the Zwicky Transient Facility, and the upcoming Vera Rubin Observatory scan the entire visible sky every few nights, flagging anything that moves unexpectedly against the background stars. Sophisticated algorithms filter the data automatically, identify outliers based on trajectory and brightness, and alert astronomers within hours or even minutes. Human observers can't process that much data. There are millions of moving objects in the solar system: asteroids, comets, artificial satellites, space debris. Sorting through them manually would take armies of people working around the clock. So we built machines to do it for us, and those machines are getting better every year. We're not smarter than astronomers were in 1990. We're just watching more carefully, more systematically, with better tools running continuously. The objects were always there, passing through, invisible simply because no one was looking in the right place at the right time with sensitive. Enough instruments. Now we are, and the floodgates are opening. But here's the twist. We expected interstellar objects to be common but uniform. The reasoning was simple. The laws of physics are universal. Star systems form through similar processes everywhere. Comets and asteroids should be similar everywhere. Maybe some variation in composition depending on the parent star's metallicity. Maybe size distributions that differ slightly, but fundamentally similar objects. We thought we'd find a lot of objects that looked like our own comets and asteroids, just coming from different home systems. Instead, we're finding extreme diversity. Oumuamua was bizarre, tumbling chaotically end over end every 7.3 hours, suggesting an elongated shape unlike any asteroid or comet we'd seen, accelerating without visible outgassing, implying some mechanism was pushing it that we couldn't detect. Completely inactive, no coma, no tail, no spectral signatures of volatiles. It defied classification. Scientists argued for months about whether it was a comet, an asteroid, or something else entirely. Some even proposed exotic hypotheses: a hydrogen iceberg, an interstellar dust bunny, even a light sail from an alien civilization, though that last idea was widely considered fringe. Borisov was normal, almost boring by comparison. A standard comet, chemically indistinguishable from solar system natives based on spectroscopy. It had a coma, a tail, active outgassing, everything you'd expect from a healthy comet making its first pass near the Sun. Observers tracked it for months and concluded it was essentially a twin to our long-period comets. If you transported a solar system comet to another star system and then sent it back, it would probably look like Borisov. Familiar, predictable, unremarkable, except for its hyperbolic orbit proving it came from elsewhere. And now, 3I Atlas. Thermally processed, chemically anomalous, exhibiting behaviour neither Oumuamua nor Borisov showed. It started active, became inactive, turned a colour we rarely see, and may or may not be fragmenting depending on which camp's interpretation you believe. It looks nothing like either of its predecessors. 3 objects, 3 completely different profiles. That's not a representative sample, that's a warning shot. It tells us that the galaxy is ejecting debris from a huge variety of environments, and we're only seeing the beginning of that diversity. Young stars eject pristine material from their protoplanetary disks. Old stars eject processed material from their depleted planetary systems. Stable systems eject objects from their outer clouds through gentle gravitational perturbations. Chaotic systems eject objects from their inner regions through violent planetary migrations. Rocky planets contribute metal-rich fragments through collisions. Icy giants contribute volatile-rich comets through orbital instabilities. Everything gets ejected from every kind of environment, in every stage of evolution. And all of it is passing through our solar system constantly, most of it too small or too fast to detect. Every year, hundreds or thousands of interstellar objects probably cross through, ranging from pebbles to mountains, moving at speeds that make detection nearly impossible. The ones we catch are the lucky ones, the ones that happen to pass close enough and slow enough for our instruments to resolve. But they're not representative. They're outliers, visible only because they're large enough, bright enough, or weird enough to stand out against the background. This has profound implications for planetary science. We thought we understood comet formation because we've studied solar system comets for centuries. We have models, refined over decades, that explain how icy bodies condense in the outer reaches of protoplanetary disks, how they accumulate volatiles, how they get perturbed into long-period orbits that eventually bring them sunward. But those models are based on one sample, our solar system, one environment, one stellar history, one formation sequence. Now we're getting samples from dozens, potentially hundreds of other systems, each with its own formation history, its own chemical evolution, its own ejection mechanisms. And they're teaching us that our models are too narrow, too local, too dependent on the specific conditions of our sun and our planets. Planetary formation is more diverse, more chaotic, messier than we assumed. And if that's true, if every stellar system produces its own unique population of debris with its own characteristics, then understanding the full picture will require cataloguing hundreds or thousands of interstellar visitors, building statistical models of the galactic population, learning from the diversity rather than trying to fit everything into frameworks built from a single example. 3i Atlas is not an anomaly, it's a data point in a distribution we're just starting to map. And the distribution is wider, stranger, and more interesting than we imagined. But to understand what 3i is really telling us, we need to talk about dust, because dust physics is where a quiet revolution has been happening, and it changes how we interpret everything. Part 12. Breakthroughs in dust physics that change the story. It looks simple, feels simple, seems like the most basic component of the cosmos. Just tiny particles floating in space, right? Dead matter, inert grains, the boring backdrop to the exciting physics of stars and planets. But light interacting with dust is fiendishly complex. One of those problems in physics that sounds straightforward until you actually try to calculate it. Then you realise you've walked into a mathematical nightmare that has kept physicists employed for generations. The way a dust grain scatters sunlight depends on its size, shape, composition, surface texture, orientation, and the wavelength of the incoming light. Change. Any one variable and the scattering behaviour shifts dramatically. Spherical grains scatter light differently than jagged grains. A perfectly smooth sphere follows predictable me-scattering theory, something you can actually solve with equations. But show me a perfectly spherical dust grain in nature. They don't exist. Real grains are irregular, asymmetric, covered in tiny pits and protrusions that scatter light in directions no simple equation predicts. Silicate grains behave differently than carbonaceous grains. Metallic grains behave differently still. Each material has its own complex refractive index, describing how light slows down and bends when entering the material, and that index varies with wavelength. So blue light interacts with a grain differently than red light, not just because of size effects, but because the material itself responds differently to different energies of photons. Tiny grains, smaller than the wavelength of visible light, scatter blue light efficiently through Rayleigh scattering, the same physics that makes Earth's sky blue. These grains preferentially redirect short wavelengths, while letting longer wavelengths pass through relatively unaffected, making objects look white or bluish when small dust dominates. Large grains scatter red and yellow light preferentially, making objects look warm-toned, shifting toward oranges and golds as grain size increases. And when you mix grain sizes, shapes and materials together in varying proportions, which is what actually happens in nature because comets are messy, the resulting colour can be almost anything. The colour space available to dusty objects is enormous, and predicting where any particular object will fall in that space requires knowing the detailed grain properties, which we almost never know with precision. For decades, astronomers assumed comet dust was fairly uniform. Small grains, maybe a few microns across, mostly silicates with some organics mixed in, fluffy aggregates loosely bound together like microscopic dust bunnies. That assumption worked reasonably well for most observations. Models based on it could explain the colours we saw in comet tails, the brightness variations as comets rotated, the way tails separated into distinct dust and gas components. It was a useful approximation, good enough for most purposes, but it didn't explain gold. Gold coloration in reflected sunlight requires very specific grain properties that simple uniform dust models couldn't reproduce. You can't get that warm, metallic, burnished appearance from a random mix of small particles. The physics doesn't work. Gold coloration in reflected sunlight requires very specific grain properties that simple models couldn't reproduce. The grains need to be large, at least 10 to 50 microns, maybe larger. approaching the size of fine sand or table salt crystals. At that scale, they're starting to become visible to the naked eye if you could hold them. They need to be highly reflective, not fluffy or porous like the standard model assumed, meaning they're either compact mineral grains that have been compressed or sintered, or possibly contain metallic inclusions that enhance reflectivity. Iron-bearing minerals, metallic nickel, polished silicates, anything with a high albedo that bounces light efficiently, and they need to dominate the reflected light completely, meaning there's no gas emission diluting the colour, no small dust adding blue or white tones, nothing else in the field of view muddying the signal. That's a very specific, very narrow set of conditions. Everything has to align perfectly to produce that golden hue. And until recently, laboratories couldn't model it accurately because the computational power required to simulate light scattering from irregular large grains in realistic mixtures was prohibitive. You need to solve Maxwell's equations for electromagnetic radiation, interacting with complex three-dimensional structures at scales where you can't use simple approximations. Early attempts ran on supercomputers for days and still only managed to model a few dozen particles in idealized geometries, nowhere near enough to understand real comet dust populations containing billions of grains in chaotic mixtures. Then, in 2023, a team at the University of Arizona published results from high-resolution dust scattering experiments using real cometry analogues. Not computer simulations, though they did those too, but actual physical experiments. They synthesized materials matching the composition of meteorites, and returned comet samples from missions like Stardust, ground them into particles of controlled size ranges using precision mills, and tested how they scattered light under various conditions in vacuum chambers designed to mimic space. They tested irregular grains, fluffy aggregates, compact grains, metallic inclusions, surface coatings, mixed populations, everything they could think of. Hundreds of experimental runs, each carefully calibrated and measured with spectrometers covering ultraviolet through infrared wavelengths. And they found that gold reflection emerges reliably when large compact grains dominate the size distribution, especially if those grains have metallic or high albedo silicate surfaces. It wasn't one magic grain type. Multiple compositions could produce the effect if the grains were large enough and reflective enough. The key was size distribution. You needed a population dominated by grains in the 10 to 100 micron range, with minimal contribution from smaller particles. Get that right. And gold appeared consistently across different mineral types. The colour isn't exotic. It's not some strange chemistry or unknown process requiring bizarre formation conditions. It's just rare because it requires a specific grain size distribution that only happens under limited circumstances. Specifically, the small dust has to be removed or blown away, leaving only the large grains bound to the nucleus. Small dust gets carried away easily by gas jets during active outgassing, or by radiation pressure from sunlight, which pushes on particles proportional to their cross-sectional area, but only resists gravity proportional to their mass. Smaller particles have higher area-to-mass ratios, so radiation pressure affects them more strongly, blowing them away from the comet into the tail. Large grains, being heavier, stay put, unless the gas flow is extremely vigorous. So gold coloration appears when outgassing has declined to the point that small dust production stops, but the object still has large grains coating its surface reflecting sunlight. This explains 3I's timing perfectly. The green phase was gas-dominated, small dust mixed with volatiles, typical comet appearance. Carbon molecules breaking apart under solar ultraviolet radiation emitted green light. Small dust scattered sunlight, diffusely adding white tones, the whole mess creating the classic fuzzy green comet look we've seen countless times. As the volatiles depleted, the gas pressure dropped and the small dust production stopped. No more gas jets meant no more mechanism for creating small particles through fragmentation and erosion. Residual gas jets carried away whatever small dust was still present on the surface, sweeping it clean like cosmic housekeeping. What remained were large grains weakly bound to the nucleus by gravity, too heavy for the dying gas jets to lift, but still present on the surface. Those large grains now dominate the reflected light, and they reflect gold because of their size and composition. It's not magic, it's optics, light-scattering physics applied to a specific particle size distribution that emerges naturally during the late stages of cometary activity. But it took decades of laboratory work and advances in computational modelling to confirm this. And even now, most of the astronomy community hasn't fully absorbed the implications because the papers are dense, technical, and buried in specialised journals that practicing observers don't typically read. The relevant research was published in Icarus and the Planetary Science Journal, respected venues in planetary science, but not high profile enough to generate press releases or widespread attention in mainstream astronomy. Science reporters didn't pick it up. No press conferences were held. The knowledge exists, validated and peer-reviewed, replicated by independent groups, but it hasn't percolated through the field yet. Most observers tracking comets don't know this framework exists, so when they see gold coloration, they're still treating it as mysterious rather than recognizable. This is how science actually progresses in practice, not through dramatic announcements at press conferences with flashbulbs and headlines, but through slow, grinding accumulation of data and theory that eventually flips a field's assumptions once enough people become aware of it and start using the new framework. Someone runs experiments, publishes in a specialized journal, a few experts read it and cite it. Gradually the ideas spread through conferences and collaborations, and eventually it becomes common knowledge. But that process takes years, sometimes decades. The gold colour was mysterious until it wasn't. And now that we understand the dust physics at a fundamental level, we can retroactively explain other observations that didn't make sense before. Researchers can go back through archival data from previous comets, observed over the past 50 years, identify other cases that briefly turned gold before fragmenting or fading, and realise we've been seeing this pattern for years without recognising it for what it was because we lacked the framework to interpret it. The data was there all along, sitting in archives, but without the theoretical understanding to make sense of it, it was just another unexplained observation in a field full of unexplained observations. Now we know. And that knowledge transforms how we interpret not just 3i Atlas, but potentially dozens of other objects going forward. Understanding dust physics only matters if we can detect the objects displaying these behaviours in the first place, and that's where artificial intelligence is changing everything. Part 13. AI now spots anomalies. Humans miss. Every night, survey telescopes capture millions of images containing thousands of objects each. That's not hyperbole. Modern wide-field survey instruments like the Zwicky Transient Facility image the entire visible sky every few nights, generating roughly a terabyte of data per night. The Vera Rubin Observatory, when it comes fully online, will produce something like 15 terabytes per night, every single night. That's more data than the entire astronomy community generated in the first 300 years of telescopic observation, now flowing in faster than humans can download it, let alone analyse it meaningfully. Every object in those images needs to be tracked, its position measured to sub-arc-second precision, classified as asteroid or comet or galaxy or variable star, cross-referenced against known catalogues containing millions of previously observed objects, and checked for unexpected behaviour that might indicate something interesting is happening. Humans can't keep up. We tried for decades, recruiting amateur astronomers through programs like Galaxy Zoo, building citizen science projects to distribute the workload across thousands of volunteers worldwide who would spend their evenings clicking through images, classifying galaxies, marking potential supernovae. Those efforts were noble and genuinely useful, generating real science, leading to discoveries that professional astronomers working alone would have missed. But it's not enough. Not anymore. The data stream is too fast, too dense, too overwhelming for human processing speeds. Even when you recruit thousands of volunteers, a human can maybe classify a few hundred objects per hour if they're working quickly and not being too careful. An algorithm can classify millions per hour, running continuously, never sleeping, never taking breaks, never getting bored or distracted. The scale difference is so extreme that human analysis is increasingly becoming a bottleneck, a limiting factor in what we can learn from our own instruments. So we built machines to help. Artificial intelligence is not magic, and it's certainly not conscious, despite what science fiction and marketing departments might suggest. It's pattern recognition at industrial scale, mathematical algorithms trained on known examples, learning to identify similar patterns in new data through statistical optimization. You feed the algorithm millions of images of asteroids, showing it what asteroids look like in various orientations and lighting conditions. You show it comets, galaxies, supernovae, satellites, cosmic rays hitting detectors, all the things that appear in astronomical images. You teach it to recognise those patterns through supervised learning, where humans label examples and the algorithm adjusts its internal parameters to match human classifications. And then you let it loose on the incoming data stream to flag anything interesting. Anything that matches known categories, or, more importantly, anything that doesn't match and might therefore be something new. The algorithm doesn't understand what it's looking at. It doesn't know that a comet is a chunk of ice and rock sublimating in sunlight, or that a galaxy is billions of stars held together by gravity. It doesn't have intuition about physics, curiosity about how things work, or insight into what makes observations scientifically significant. It just compares patterns against templates, looking for matches and mismatches, and highlights outliers, objects that don't fit comfortably into expected categories. It's doing statistics, not science. But that statistical filtering is exactly what we need, because discoveries hide in outliers. The truly interesting phenomena, the ones that advance fields and overturn assumptions, are the ones that don't fit existing models, the objects behaving in unexpected ways that force us to expand our understanding. And machines are excellent at finding those because they don't get bored, don't get tired, don't unconsciously filter data based on preconceptions about what's important or what's worth investigating. A human observer might look at an unusual light curve and dismiss it as instrumental noise or bad data because it doesn't look like anything they've seen before. An algorithm doesn't have those biases. It just flags the deviation and moves on to the next object. 3i Atlas was flagged by an AI system before human astronomers confirmed it as interstellar. The Asteroid Terrestrial Impact Last Alert System, which gives us the Atlas acronym, runs machine learning algorithms on all detections, calculating orbital parameters from the sequence of positions measured across multiple nights, comparing those trajectories against databases of known objects containing everything from near-Earth asteroids to distant Kuiper Belt objects, flagging anything with unusual orbits. The algorithm noticed 3i's trajectory didn't match any known object in the database. More importantly, it calculated that the orbit was hyperbolic, unbound, meaning the object was travelling faster than solar escape velocity and would eventually leave the solar system rather than returning on a periodic orbit. That's the signature of an interstellar origin, an object that came from outside and is just passing through. The algorithm raised an alert within hours of detection, automatically notifying a network of professional astronomers that something potentially significant had been found. Human astronomers then performed follow-up observations using different telescopes to confirm the AI's assessment, verify the orbital elements through independent measurements, rule out measurement errors or computational glitches that might have produced a false positive. But the initial discovery, that crucial moment when 3i went from being just another anonymous streak in an image to a potentially significant object worthy of immediate attention and dedicated observation time, that was machine-driven. A human might have found it eventually, but the AI found it faster, more reliably, and with less chance of it slipping through unnoticed. Now, AI systems are getting better, more sophisticated in what they monitor beyond simple positional tracking. They're not just flagging objects based on orbital parameters anymore. They're analysing light curves for anomalous brightness variations that might indicate rotation, outbursts, or fragmentation. They're studying spectra for unusual emission line ratios that don't match standard comet or asteroid compositions. They're tracking colour changes over time, watching for transitions like the green to gold shift that 3i exhibited. They're correlating observations across multiple wavelengths, looking for objects that appear bright in infrared but faint in visible light, or vice versa, signatures of unusual temperatures or compositions. Anything measurable, anything that can be quantified and compared, the algorithms are watching. They're spotting correlations humans would never notice, because humans don't naturally think in 20-dimensional parameter space, where relationships between variables become apparent. We can visualize 2 dimensions easily, 3 with some effort, maybe 4 if we use colour and size as additional variables in a plot. But modern astronomical data has dozens of measured properties per object: position, velocity, brightness in multiple filters, spectral features across hundreds of wavelengths, variability timescales, morphology parameters. The relationships between all those variables simultaneously define a high-dimensional space that human intuition can't navigate. But algorithms can. They treat it as straightforward linear algebra, projecting the data into that space, and looking for clusters, gaps, outliers, anything unusual. If there's a pattern where green comets in specific sky regions are statistically more likely to turn gold, an AI will find it by analysing the full historical dataset systematically, comparing thousands of comet observations and looking for correlations between colour change and sky position that individual observers might not notice. If there's a correlation between heliospheric sector position and fragmentation events, an AI trained on decades of comet observations combined with solar wind data from spacecraft will identify it, connecting datasets that researchers traditionally kept separate because they came from different subfields. If there's something about 3I's behaviour that mirrors an obscure object catalogued 50 years ago and mostly forgotten, except as a line in a database, an AI will retrieve that information and flag the similarity, connecting observations across decades that no human researcher could remember or cross-reference manually. This is both exciting and unsettling. Exciting because it means we're about to discover patterns that were always present in our data, but too subtle for human perception, connections invisible to individual researchers working within their specialised subfields, but obvious when you look at the aggregate data across the entire field. We'll learn things about how comets behave, how stellar systems eject material, how interstellar space affects objects during transit, simply because machines can see relationships in data that we can't. Correlations that were always there, written in the observational record, but that required computational power and algorithmic sophistication to extract. But it's also unsettling, genuinely uncomfortable for many scientists, because we don't always understand why the AI is flagging something. Modern machine learning, especially deep learning neural networks with millions of parameters, operates as black boxes. You can see the inputs, the raw data going in, you can see the outputs, the classifications and alerts coming out, but the internal decision-making process is opaque, hidden in layers of mathematical transformations that are technically explicable, but practically incomprehensible. The AI sees a correlation, identifies an outlier, raises an alert, but it can't explain in human terms why it thinks something is important. It can't say, I noticed this because the dust-to-gas ratio is unusual, or this reminds me of Comet X from 1973. It just outputs a probability score and moves on. It hands us a mystery and says, this looks interesting, figure it out. And we have to decide whether to trust it, whether to invest limited telescope time, which is precious and oversubscribed with astronomers competing for every available hour, and researcher, effort following up on a hunch generated by an algorithm that can't justify itself in terms we understand. Sometimes the AI is wrong, flagging statistical noise or instrumental artifacts as significant. Sometimes it's right, pointing toward discoveries we would have missed. Learning to calibrate that trust, to know when the AI is worth listening to, is one of the challenges facing modern astronomy. 3I Atlas is already anomalous by AI standards. Multiple independent machine learning systems analysing sky survey data from different telescopes have flagged it for priority follow-up. Not just because it's interstellar, though that alone would be sufficient reason for intense observation, given how rare these objects are, but because its behaviour stacks multiple low-probability events in ways that raise statistical red flags. Rapid colour change, happening over days rather than the weeks or months models predict. Position in Leo during the transition, coinciding with K1 Atlas's similar behaviour. Temporal coincidence with K1, both objects turning gold within weeks of each other. Spectral anomalies showing nickel without iron, chemistry that shouldn't happen according to standard formation models. Dimmer than predicted for its estimated size, suggesting either our size estimate is wrong or the object is losing mass. Any one of those is interesting, worth a follow-up observation or two. All of them together in a single object is statistically suspicious, the kind of combination that makes algorithms throw warnings, because the probability of all those things happening together by chance is very low. The AI doesn't know what it means. It doesn't have a theory about heliospheric sectors or thermal processing or environmental triggers. It just knows that when you train a pattern recognition system on decades of normal comet behaviour, objects that follow predictable patterns, and then show it 3I, the system throws warnings saying, this doesn't fit the pattern, this is an outlier, pay attention to this, and maybe that's enough. Maybe that's exactly the right division of labour. Maybe the job of AI in astronomy is not to explain, which requires physical understanding and creative theorising that algorithms can't do, but to point, to direct human attention toward phenomena worth investigating, to act as a filter separating the potentially significant from the routine. And the job of humans is to bring domain expertise accumulated through years of studying planetary science, physical intuition about how materials behave under various conditions, and creative hypothesis generation to figure out what the patterns mean, to build explanatory models that connect the observations to underlying physics. It's a partnership, and it's reshaping how astronomical research gets done in practice, changing the workflow from human discovers then human analyzes to machine discovers then human analyzes. So we investigate. We turn telescopes toward 3i, scheduling observations at observatories worldwide. We coordinate across continents, ensuring that as Earth rotates and different parts of the sky become visible from different longitudes, someone somewhere is watching, collecting data continuously. We prepare for December 19th with an intensity usually reserved for major solar system events like spacecraft arrivals or predicted asteroid close approaches, mobilizing resources and expertise because this opportunity won't come again. And we hope the AI is wrong, that this is all coincidence, that the patterns are statistical noise that looked meaningful by chance, but will fade away as we collect more data and realize there's nothing special happening after all. But we also prepare for the possibility that the AI is right, that something genuinely unusual is happening with this object, that we're about to understand a process we couldn't see before because we weren't looking at the data the right way, weren't making the right correlations, weren't asking the right questions, and that's the promise of AI in science. Not replacing human researchers, but augmenting them, helping us see what was always there but invisible to unaided human perception. But 3i's journey isn't over on December 19th. It passes Earth, and then it keeps going, deeper into the solar system, toward Jupiter. Part 14, Jupiter, the next test. It's a gravitational tyrant, a cosmic bully that reshapes anything passing within its sphere of influence. Its gravity is so immense, so dominant, that it warps the trajectories of comets and asteroids throughout the solar system, flinging some into the sun on death spirals, ejecting others into interstellar space at velocities high enough to escape the solar system entirely, capturing a few into its own orbital family where they become Jupiter family comets locked in predictable cycles. Jupiter's mass is 318 times Earth's mass, containing more matter than all the other planets, moons, asteroids and comets in the solar system combined. But it's not solid rock or metal like Earth. It's a gas giant, mostly hydrogen and helium, the same materials that make up stars, just not quite massive enough to ignite fusion. That mass is concentrated in a relatively small volume compared to a rocky planet of equivalent mass, creating gravitational effects strong enough to matter at surprising distances, far beyond where you'd expect a planet's influence to reach. Jupiter shapes the architecture of the entire solar system. It's why the asteroid belt exists as a belt rather than coalescing into a planet. Jupiter's gravity stirred that region too violently for a planet to form, keeping the asteroids scattered and colliding rather than gathering into a single body. It's why certain orbital resonances in the Kuiper belt are empty, swept clean by gravitational perturbations that eject objects over millions of years. It's why we see the comets we do, their orbits bent and redirected by repeated Jovian encounters that gradually shift their paths until they either escape or crash into something. Jupiter is the solar system's gravitational architect, sculpting the debris field around the Sun through nothing but the patient, relentless pull of its enormous mass. In 1994, we watched comet Shoemaker-Levy 9, broken into more than 20 distinct fragments by a previous close pass to Jupiter in 1992, crash into the planet's atmosphere in a series of spectacular impacts that left Earth-sized dark scars visible for months afterward. Each fragment hit with the energy of millions of nuclear weapons, creating fireballs that rose thousands of kilometers above Jupiter's cloud tops, leaving bruises in the atmosphere larger than our entire planet. Astronomers worldwide turned their telescopes toward Jupiter, watching impact after impact over the course of a week as the fragmented comet train ploughed through the Jovian atmosphere. It was the first time humans had witnessed a cosmic collision in real time, predicted in advance, observed from beginning to end. And it demonstrated viscerally what Jupiter's tidal forces can do to a fragile object that ventures too close. In 2020, we watched Comet Atlas, Not the same Atlas survey family, but an unrelated object that happened to share the acronym, fragment as it approached the Sun, possibly destabilized by Jupiter's influence during an earlier past years before that had weakened its internal structure. The fragmentation wasn't immediate. The comet had survived its Jupiter encounter, apparently intact, and continued inward toward perihelion. But the damage was done. Cracks had formed, internal stresses had accumulated, and when solar heating began sublimating ices, the weakened nucleus couldn't hold together. It came apart gradually, splitting first into 2 pieces, then 4, then more, each piece continuing to fragment until the comet was a dispersed cloud of debris rather than a single object. Jupiter had killed it, but slowly through wounds that took time to prove fatal. Jupiter doesn't just attract objects, it tears them apart through tidal forces, stresses them through gravitational gradients that stretch and squeeze simultaneously, and fundamentally alters their orbits and internal structures in ways that can take years or decades to manifest fully. It's not a gentle giant. It's dangerous, especially to small, fragile bodies that lack the structural integrity to withstand forces that would be negligible to a moon or large asteroid, but are devastating to a loosely bound comet nucleus. 3I Atlas will encounter Jupiter in late 2026, approximately 18 months from now, assuming current trajectory calculations are accurate, and no unexpected non-gravitational forces alter its path. Not a close encounter by Shoemaker-Levy standards, where the comet passed within Jupiter's Roche limit and was literally pulled, apart by tidal forces exceeding its self-gravity, but close enough to matter, close enough to be significant. The object will pass within 2 astronomical units of the gas giant, roughly 300 million kilometers, about twice the distance between Earth and the Sun. That might sound safe, might seem like plenty of clearance, but it's well inside the zone where tidal forces become significant for a fragile, loosely bound nucleus held together more by frozen volatiles acting as glue than by any substantial self-gravity or structural strength. If 3I survives its December 19th passage intact, if it holds together through Earth flyby without fragmenting and remains a single coherent object rather than a dispersing cloud of debris, Jupiter will be the second test. A very different kind of test. A test of structural integrity under gravitational stress rather than thermal stress, where the Sun tests an object through heating, sublimation, and thermal expansion. Jupiter tests through pure mechanical force, pulling and stretching, probing for weaknesses in the internal structure. A test of whether an interstellar comet, thermally processed and volatile depleted, potentially more like a rocky asteroid than a traditional ice-rich comet, can withstand the pull of the solar system's most massive planet. Tidal forces work through differential gravity. The fact that gravity isn't uniform across an extended object when that object is in a strong gravitational field. Jupiter pulls more strongly on the side of an object facing it than on the far side, simply because the near side is closer and gravity decreases with the square of distance. For a small object a few hundred meters across passing a few 100 million kilometers from Jupiter, this difference might be only a few percent of the total gravitational force. But that few percent matters enormously if the object is weak. For a large cohesive object like a moon, or a well-integrated rocky asteroid with substantial internal strength, materials mechanically bonded together through sintering or compression, this difference is negligible, easily resisted by the material's tensile strength and structural integrity. Moons orbit Jupiter at much closer distances than 3I will pass, and they don't fall apart because they're strong enough to resist the tidal gradient. But for a small, loosely bound rubble pile like most comets, where the components are only barely held together by weak self-gravity and whatever cohesion frozen ices provide, it's devastating. The near side of the comet wants to fall toward Jupiter, accelerating toward the planet faster than the centre of mass. The far side wants to stay back, falling slower than the centre of mass. The middle gets pulled in both directions simultaneously, stretched like taffy between 2 opposing forces. If the object's tensile strength, its ability to resist being pulled apart, can't overcome this stretching stress, if the forces trying to separate the pieces exceed the forces holding them together, it comes apart. Not explosively with violence like a bomb detonating because there's no sudden energy release, but steadily, almost gently, fragments drifting away from each other at speeds of meters per second as the tidal gradient overcomes whatever weak gravity or ice cementation was holding them together. Will 3I survive? That's the billion-dollar question, literally given how much telescope time and research effort will be invested in finding out. If it's already as fragile as the baked core hypothesis suggests, if the gold colour truly indicates a dust-dominated relic with minimal internal cohesion, if the volatile ices that once held it together are gone, and all that remains is a loose pile of dust and rock barely touching, then Jupiter will finish what the Sun started. We'll see the object disintegrate over weeks, not instantaneously, but progressively, fragments spreading into a debris stream that gradually elongates along the orbital path, eventually dispersing into the solar system's background population of dust and small particles, indistinguishable from ordinary cometary debris after a few years once it's spread too thin to track. But if 3I is denser than we think, if our estimates of its mass and composition are wrong, if the thermally processed interior has been sintered into a more cohesive structure through repeated heating and cooling cycles over millennia or millions of years in its home system, then it might pass through Jupiter's influence unscathed. Not completely unaffected, certainly. Scarred, perhaps, with some surface material stripped away by the gravitational stress, loose dust and small particles pulled off into space. Altered in orbit, definitely, because Jupiter's gravity affects everything that passes nearby, bending trajectories, changing velocities, redirecting paths, but fundamentally intact, nucleus still bound together as a single object, still recognizable as the same comet that entered the solar system, still trackable as it exits back into interstellar space. And then there's the radiation environment, which adds another layer of complexity and potential danger. Jupiter's magnetosphere, the magnetic bubble surrounding the planet created by its internal dynamo, the churning metallic hydrogen in its interior generating powerful magnetic fields, is brutal. It's the largest coherent structure in the solar system, aside from the Sun's heliosphere itself, extending millions of kilometers into space far beyond the orbits of Jupiter's major moons. Charged particles, electrons and ions from the solar wind and from volcanic activity on Jupiter's moon, Io, get trapped in this magnetic field and accelerated to extreme energies, creating radiation belts far more intense than Earth's Van Allen belts. The radiation environment around Jupiter is one of the harshest in the solar system. For a human, exposure at close range would be lethal in hours, maybe less, with radiation. Doses measured in hundreds of thousands of rads, enough to destroy cellular function and cause immediate radiation sickness even with protective equipment. For spacecraft, the radiation is a serious engineering challenge, requiring radiation-hardened electronics, special shielding, careful trajectory planning to minimize time spent in the most intense regions. NASA's Juno spacecraft, currently orbiting Jupiter, was specifically designed to survive this environment, with its sensitive electronics housed in a titanium vault to shield them from radiation. For a comet, exposure might accelerate surface erosion through sputtering, a process where high-energy particles slam into surface atoms with enough force to knock them loose, ejecting them into space molecule by molecule. It's like sandblasting at the atomic level, gradually wearing away the surface over time. It might ionize surface materials, stripping electrons from atoms and creating charged dust particles that behave unpredictably, repelling each other electrostatically because they carry the same charge, or responding to magnetic fields rather than just gravity, potentially creating unusual tail structures or asymmetries in the coma. It might trigger chemical reactions in any remaining surface ices, providing energy for chemistry that wouldn't happen otherwise, forming new compounds we wouldn't see in normal comet observations. Radiation can break molecular bonds, create free radicals, enable reactions between species that normally wouldn't interact. We've studied this in laboratory settings, irradiating ice samples and analysing what forms, but we've never observed it happening on an actual comet in Jupiter's magnetosphere. We've never tracked an interstellar object through Jupiter's magnetosphere before. This would be unprecedented. We genuinely don't know what to expect. Maybe nothing visible. Maybe the effects are too subtle to detect with current instruments, requiring dedicated spacecraft at close range to measure rather than telescopic observations from Earth. Maybe something spectacular that shows up clearly in observations, unusual spectral features, brightness variations, morphological changes that tell us something fundamental about how radiation interacts with cometary materials. 3i Atlas's encounter with Jupiter won't happen for more than a year, a long wait from December 2025 to late 2026. But it's already on the calendar, already being planned for by research teams worldwide. Observatories are already modelling the trajectory using current orbital parameters, calculating closest approach distances, running simulations of how Jupiter's gravity will bend the path, estimating the tidal stress magnitudes the nucleus will experience. They're scheduling telescope time contingent on the object remaining trackable, that long, requesting observation windows a year in advance because major facilities are booked far ahead. Researchers are already building models predicting what happens under different scenarios: intact passage where the object survives structurally sound, partial fragmentation where it breaks into a few large pieces but doesn't fully disperse, complete disintegration where it shatters into countless small fragments and ceases to exist as a discrete object. Each scenario makes different predictions for brightness evolution, fragment trajectories, long-term observability. Each requires different follow-up strategies and instrument configurations, because whatever happens on December 19th, whether 3i breaks apart during its Earth flyby or holds together and continues inward, Jupiter will be the follow-up act. The second chapter in a story we're still writing in real time, the next major test of this visitor from another star, and the answer we get, whether the object survives or disintegrates, will tell us something fundamental about the internal structure of thermally processed interstellar objects, information we can't get any other way except by watching and waiting, tracking this single object through the solar system's most challenging gravitational environment, and seeing what happens. And that brings us to the final question, the one we'll still be asking long after 3i has faded from view. Part 15. The question we'll still be asking. Next year. Let's imagine 3i Atlas survives. Let's say December 19th arrives, observers worldwide turn their instruments toward the golden visitor, and the data shows stability. Brightness holds steady. No fragmentation features appear in high-resolution imaging. Spectroscopy remains consistent. The object passes Earth at 42 million kilometers, glowing gold in the darkness, intact and coherent. Let's say it continues through the inner solar system, encounters Jupiter in 2026 without incident, and eventually exits back into interstellar space on its hyperbolic trajectory. A little dimmer perhaps, a little altered by solar heating and Jupiter's gravitational nudge, but fundamentally whole. What then? We still don't know why it turned gold. We still don't have a complete explanation for the nickel without iron chemistry, beyond tentative carbonyl hypotheses that remain unconfirmed. We still can't explain with confidence the temporal coincidence with K1 Atlas, or why both objects pass through Leo while exhibiting identical colour transitions. We still lack a predictive model that tells us when rapid colour changes should occur in thermally processed interstellar comets, and we still haven't answered the deeper question at the core of this entire story. What phase did 3i Atlas enter when it lost its green coma? Is this a standard evolutionary stage that appears in all comets under the right conditions, something we've simply never documented clearly because it's rare and brief? Or is this something unique to interstellar objects, a behaviour that emerges specifically in thermally processed bodies that have travelled through the cosmic void for millennia? Conversely, let's imagine 3i fragments. Let's say the object breaks apart on or around December 19th, or maybe a few days later, scattering into a debris cloud that grows and fades over the following weeks. Multiple brightness peaks appear in images where there was one before. The fragments diverge along slightly different trajectories, spreading into an elongated stream. Brightness drops as the total surface area decreases. Within a month, 3i is no longer a single trackable object, but a diffuse cloud of rubble gradually dispersing into the solar system background. We still don't know why. Was it thermal stress from solar heating? The last volatiles venting and creating internal pressure that fractured the weakened structure? Was it tidal stress from an earlier close approach we didn't detect, perhaps during its inbound journey before we discovered it, cracks propagating slowly until they finally breached? Was it structural weakness inherent to its thermally processed origin, a nucleus so depleted and fragile that any stress was sufficient to break it? Was it environmental factors related to heliospheric position, charged particle bombardment or magnetic turbulence enhancing erosion, or weakening cohesion? All of the above, none of the above, And if we can't determine the cause, can't isolate the mechanism with confidence even after watching it happen, in real time with optimal observing conditions, what does that say about the current state of our understanding of comet physics? Either outcome leaves us with questions. Survival raises different questions than fragmentation, but both scenarios leave gaps in our models. Phenomena we can describe but not fully explain. And maybe that's the point. Maybe 3i Atlas isn't here to answer our questions. Maybe it's here to show us which questions we should have been asking all along but weren't, because we built our models on insufficient data from a single stellar system. The gold colour, the Leo coincidence, the Cave 1 parallel, the nickel anomaly, these aren't separate mysteries. They're threads in the same tapestry, clues to a process or processes we haven't fully characterised yet. Maybe it's a rare but natural stage of comet evolution that appears under specific conditions we can now start to identify. Maybe it's an environmental trigger sensitive to location and timing in ways our current models don't account for. Maybe it's something entirely mundane that looks exotic only because our observational data has been incomplete and we're seeing clear examples for the first time. Or maybe, just maybe, it's something genuinely new, a behaviour unique to interstellar objects, a signature of their alien origins and the strange environments they pass through before arriving in our neighbourhood. We're living through the Golden Visitor's Passage right now, this week, these days, December 19th. 2025 will be remembered, if everything goes according to plan, as the date when 3i Atlas made its closest approach to Earth. Astronomy papers will cite it, future textbooks might mention it, but the real legacy, the thing that will matter decades from now when we've catalogued hundreds of interstellar objects and built statistical models of the galactic population, will be the questions it left behind. Not the answers, because we don't have complete answers yet. The questions. The objects we don't fully understand are the ones that teach us the most. They force us to examine our assumptions, test our models against unexpected data, expand our frameworks to accommodate new phenomena. 3i Atlas, tumbling through the inner solar system at this moment, glowing gold against the background stars, defying easy classification and comfortable predictions, is teaching us that the universe is stranger, more diverse, and vastly more interesting than we allowed ourselves to imagine when we only had our own solar system as reference. So we watch, we wait, we prepare instruments and coordinate observations and build models and argue about interpretations, and we prepare to be surprised, because if there's one lesson 3i has driven home with absolute clarity, it's this. The cosmos doesn't care about our models. It doesn't consult our textbooks before deciding how to behave. It does what it does according to physics we're still learning to understand fully. And our job, the privilege and responsibility of being conscious beings, capable of curiosity and investigation, is not to be right. It's to pay attention, to stay curious, to ask better questions when the old questions prove insufficient, and to admit, when the moment demands it, when the evidence makes it unavoidable, that we don't know, not yet. But we're learning, and on December 19th we'll learn something more, something we didn't know before, something that might take years to fully understand, but that will add one more piece to the puzzle of how comets behave, how star systems form, how the galaxy distributes its debris across the cosmic ocean. One more visitor from another shore, telling its story in reflected sunlight and spectral lines, if only we're ready to listen.